Hey folks, I'm here. I'm just making some notes for some stuff before class starts, so um, I will be with you in a little bit. But feel free to ask questions or anything if you've got stuff.
Oh man, am I late?
No, you're not late. I'm just making some notes
Oh, okay.
early to before class starts because there was some stuff that was going to take a lot of writing, and I was going to try to speed things up a little bit. So nobody's late. Class doesn't start for 4 minutes. You're all good.
Oh, okay.
Sorry to freak you
Uh,
out.
Check out this puppy. It'll make your day.
Oh, I would. Oh, there we go. Oh, it's adorable. It's wearing a little blanket.
All right.
That is awesome. We appreciate the puppy fix. Okay, I will stop freaking people out and go back to just being me. And we can return to induction in a little bit. I have no puppy to share. I have a cat. The cat's not likely to come in and want to be friends. So it's not that sort of cat at the moment. So, um, so how are we doing on week 4? The beginning of week 4, a month left of classes. So we're about the halfway point between the beginning of online classes and the end of the semester. So
Getting close. Nearly done. We got 6 inches of snow here, Nick. It's
6 inches of
6 inches, yeah.
Holy
It's
moly! And
insane.
Where
where?
is that?
Mankato?
Good grief!
Yeah. And it was 70 last week one day.
Oh
And
my
and we
goodness
got
gracious!
6 inches of snow.
We have we've barely crossed 60 a couple of times. We haven't gotten to 70. We've been in the 50s sort of several times, but we've only just gotten into 60. And we had snow Thursday. We had this weird, like it was sunny and then it snowed and then there was hail and then it was sunny again and then it snowed again and then it rained a little and then it snowed some more. It was a super strange day, but it didn't amount to anything. Like I think there probably wasn't more than a quarter of an inch, maybe half an inch total, and it all melted off almost immediately.
Yeah, we still got a solid, like, there's still a solid couple inches on the ground this morning.
Oh, good grief. So, like, did they actually, like, go out and plow and stuff?
You know, I don't know if they did or not. I guess I didn't look. They must have, because the road doesn't look too bad, but like it's melting off the roads okay, but it's sticking pretty well on the grass and stuff.
Yeah. That's nuts. That is crazy. Well, Google Photos was like, here's what you took pictures of a year ago. I think it was yesterday or maybe it was Saturday, but we had a significant snowstorm here a year ago over the weekend. I don't remember the exact day. And so I had pictures of fairly heavy snow here. It wasn't 6 inches though. I mean, I think it was might have been 3 or 4, but it wasn't 6. And here yesterday was cold and windy. Like it was I think it was in the low to mid, the high was in the low to mid 30s. And the wind chill was 10 degrees below that. But it was gray, but it wasn't snowing or there was no precipitation. So, well, that's nuts. That is nuts.
Gotta love Minnesota winter.
Yeah, no joke. Well, one member of our class is from outside of Anchorage, Alaska. So they're having, you know, even weirder weather.
That's super fun.
And when they come to class, it's 6:15 in the morning for them. So you think it's early getting up for Nick talking about logic for you. Could be worse. So, okay. So we should go ahead and start. It's 9:15. We're kind of done with chapter 9. But I'm happy to take questions about chapter 9 or any of the other things. I posted I emailed everybody a link to the solutions to the second exam. So I wrote up the answers to the second exam and shared those. It became clear to me that you weren't going to get grades on those exams very soon. And so just to be, so you had something to look at in case there were, you know, questions or confusion. I wrote up all the answers and shared those. I will certainly try to get the exams when I can, but we're running pretty behind here on a whole host of things, and that's definitely one of them. So apologies for that. And there is now a new quiz, which is due Thursday on some of this chapter 12 stuff that we're starting today. And if you missed the sort of plan, we're skipping 10 and 11 for the moment. So we're jumping from 9 to 12. That's what we'll talk about today. We talked about it a little bit on Friday. Quiz due Thursday is on some chapter 12 stuff. And there's a chapter 12 assignment due a week from today. And I'm not entirely sure. I kind of feel like the way things are going that we'll do chapter 12, we'll come back to chapter 10, and that might largely be the end of the semester for us. I don't know quite how the speed's going to go. We might have time for a little stuff at the end, but I wouldn't be shocked or freaked out if in the end what we do is 12 and 10 and then we're finished with the semester. So we'll see how things go. Are there questions about any of the previous stuff, any of the exam answers that I posted, things?
I have a question about the class itself.
Yes.
So we have until the 30th now to change our grade basis, correct?
Correct. So, and that's true for all classes. I mean, there's nothing special about this, but they've moved the grade basis change date and the drop dates are now both pushed off to much closer to the end of the semester. They were originally going to be this week, and they're now sort of 2 weeks out from that. So you do still have some more time if you want. You know, I will try to get the exams back to you by sort of before, so you have time to use that information. Because at that point, we're getting close to the final, and you really ought to have your grades on the second exam before we do the final, please. So I'll certainly try to make that happen. We'll see how it goes. Unfortunately, I found that basically I just don't have any time for grading. I'm spending my whole life like in meetings and classes and you know, trying to make things work. And it's been very hard to find time to grade, even on the weekends. And and I should say, as an announcement thing, we'll be sharing links and stuff here later this week. But Saturday, so in 6 days, Saturday, the 18th, I think that is. Yes, the 18th, is the Computer Science Senior Seminar Conference. Normally, we run sort of a conference where we have rooms and a whole series of speakers on a Saturday, and we have snacks, and it's all very nice. And of course, we can't do that. So we're going to be doing a Zoomified version of this on Saturday, where there will be something like 15 to 17 speakers in 2 separate rooms running in parallel. So there'll be like 4 hours of talks. It'll be half-hour slots. That'd be 4 hours. We'll share the Zoom link. So if you want to come, and there'll be a schedule so you could come to like some of the talks and ignore other talks. Normally we really encourage folks like you to come and see kind of what senior seminars like and learn some cool things. We would still encourage that, but you know, hopefully none of you will have to give your senior sems online remotely through Zoom. So hopefully that part of the experience will be different. And frankly, who knows how the technology is going to work. We've never really tried doing something this big with Zoom. A lot of the students will be broadcasting from home with various levels of internet. So it could be an exciting Saturday, but so that's going to be happening. And one consequence of that for me is I've got I'll probably have, 8 to 10 hours of practice talks this week in the evenings, on top of everything else. So I'm not likely to get much grading done this week. So I apologize, but that's the truth of the world. So, so I don't know, Kyle, did that help?
Yeah, it did.
Other questions before we go do induction? Going. Okay, so induction for funds. I actually started by writing some things up before class, just because I wanted to, have some of the setup going, and speed things up. This completely must have been a little weird for people that joined early and thought that they, were late for class because Nick seemed to be halfway through, a lecture. But apologies if I muddled you there. So I'll start by basically repeating some of the things from the end of Friday, and then we'll actually get to doing an example and talking about what all this means. So let's consider this claim here. So P of n says that the sum of I for 1 at most I at most n 2i minus 1. So we're going to be adding 2i minus 1 over and over again for I is 1, I is 2, I is 3, I is 4 up to n, okay? So if we add up all those 2i minus 1s, we get n squared, which isn't super obvious. I don't think it would be entirely clear, to me at least, that, 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus ... say 2 times 10 minus 1, that would equal 100, right? Not clear to me that I would think that was going to be the case. So this doesn't seem to be an entirely obvious statement to me, but it turns out to be true. And we can in fact prove that it's true, that the sum from I going from 1 to n, inclusive on both ends, of 2i minus 1 is always n squared. Now, this is, to say this is true for all n, right, which is what we're doing here, for all n, p of n, we're making an infinite number of claims. We're saying p of 0 is true, p of 1 is true, p of 2 is true, p of 3 is true, and p of 100 is true, p of a billion is true, right? We're saying all these things are true. So this is an infinite collection of claims. And so how do we prove this with a finite amount of effort? How do we prove an infinite set of things without doing an infinite amount of work? Because obviously infinite work is hard to come by. And so the solution here is this idea of mathematical induction. And that's the central point of chapter 12, is to introduce this idea of induction and show us how it works. And I should point out that this example, normally I don't do examples that the book does, but in this case, I wanted to start with the example that's in the book to try to help people know how to read this part of the book, because I think that reading chapter 12 is often a challenge. We'll do examples that aren't the example in the book, but I'm actually starting with the example in the book in the hopes that it sort of helps it connect a little better, right? So do we have questions on this part of this slide before we continue on? Any questions about the setup? Going? Okay, then what are we going to do? How are we going to do this with a finite amount of effort? Well, I'm going to simplify what's in the book a lot at first, and then we'll back up and talk about how what I'm saying here matches up with what's in the book. But this is actually how we will, in practice, do this most of the time. This is what most of the proofs are actually going to look like, because the book launches into these great big nested quantifiers, and it's like, what does this mean, and why do I care, and oh my god, this is confusing. And it's really much simpler than it sounds. All that setup makes it, all the book's sort of quantifier-y setup makes it seem like this is going to be the most complicated thing ever. And it actually isn't. You really only have to prove two things, and then you're done. And they're not often hard things. I mean, they're work, but they're not like the end of the world hard things, okay? So we're going to prove all of these things, all of this stuff here. We're going to, in fact, prove just two things. We're going to prove P of 0 is true. That's this guy here, okay? And we're going to prove that P of n implies P of n plus 1 for all n, okay? And notice that the for all n there, and actually technically that would be for all n at least 0, to be careful about it. And in the book's universe, that's going to be for all n, at least, let's see, we could do, we'll say natural numbers, P of n implies P of n plus 1. So that's, how we would formally write this. This is true for all n at least 0. We can say for all natural n, or for all n where n is greater than or equal to 0, P of n implies P of n plus 1. Okay. So we're going to prove these two things. And that's all we have to do. It really is as simple as that. Now, I want to talk about why that makes sense, why proving these two things somehow proves this infinite collection of things. And then we'll go ahead and actually prove these two things for this particular example, and we'll look at some other examples. And then we'll talk about the more complicated quantifications that are in the book and why this is essentially like those, okay? So the idea here, why is it okay to just prove these two things? Well, these two things by themselves don't prove all of these infinite things, but they give us a method by which we can generate a proof of pk for any k at least 0 using these two things and transitivity, okay? So if we know these two things and we know transitivity, in fact, it's really, in the example I'm going to use, it's actually modus ponens, 377. So 377 modus ponens says that P and P implies Q implies Q. So if we know P and we know P implies Q, then we also know Q, right? And this sort of makes some sense, right? If we know P, if we think of this as being P, and this is Q, so if we know P, check, and we have a way of getting from P to Q, namely that P implies Q, check, then we can get to Q. We know that Q is true because we have the starting point, P was true, and we had this implication that said if P is true, then Q is also true. So does this little bit, does that little bit make sense? Do people have questions about that? Because that's actually a pretty important logical step for all of this induction stuff that we're doing. Okay. Then let us continue. So what's the basic idea then? If I said, I prove these two things, and that means that I can do all of this stuff. And you were like, yeah, I don't know that I believe that. Like, I don't see P of 1 anywhere here. How do we know that? And I can be like, not a problem. We know P of 0, that's right here. And we know P of 0 implies P of 1. That's this with n being 0. And since we've said that it's true for all n at least 0, n equals 0 is one of those. So I know this. So now I have P0 and P0 implies P1, which by modus ponens gives me P1. So I have a way to prove P1, even though P1's not in this, not explicitly in this pair of things. And you're like, okay, maybe. Well, what about P of 2? Because I don't see P of 2 here. And I can be like, well, I know P of 1 is true. I just proved that. You agreed that that was a thing. And I can put 1 in for n here, and I get P of 1 implies P of 2. So P of 1 and P of 1 implies P of 2 by modus ponens again gives me P of 2. Okay. And you're like, oh, okay. And now we can play this game all day, right? You can say, well, what about P of 3? And I could be, well, I've got P of 2, and I know P of 2 implies P of 3, so now I have P of 3. And I can do this sort of going out as far as I want. So I can have P of 0 and P of 1, and I have P of 0 implies P of 1, so that gets me there, and P of 2, and P of 1 implies P of 2, so that gets me there, and P of 3, and P of 2 implies P of 3, so that gets me there, and P of 4, and P of 3 implies P of 4, so that gets me there. And so obviously, if I keep going, right, I can go out as far as I want. I could get to like P of a zillion. I just need a lot of steps. It might be really tedious, but I can get there through a finite series of steps. Whatever, if you give me a finite value of K, I can do a finite set of steps that'll get me from P0 to P of K for any K, okay? And the idea then is that hopefully you're willing to sort of capitulate at this point and say, okay, fine, yes, I believe that for any N you can, or any K, that you can get there. And so I will accept that this is a proof that P of K holds for all K, because I don't want to watch you do all of these proofs, okay? Now that's a pretty weird idea. Like there's a lot of interesting math and philosophy going on there. Like, does this really constitute a proof? And there were a lot of arguments in the late 1800s and early 1900s about what it meant to be a proof and whether this actually was one. So if you're feeling a little about this, that's entirely rational. Like you know, very, very smart people had very serious, debates about this kind of stuff. It is generally accepted that this is a legitimate proof rule, and most mathematical proof systems include some kind of induction, but it's not, I don't think you should consider this to be obvious or like, well, of course I should understand this and I can't possibly have any questions about this. I think there's a lot of very legitimate questions to be asked here. So are there any questions about this before we then look at actually doing a proof?
Yeah, I got a question.
Go for it.
So if you go back up to the two things that you need to prove,
Yep.
you have the base case, and then how are you coming up with that second thing that you need to prove? I guess I'm not entirely following that.
Well, and I should label these. So this is, as was just stated, this first one is usually called the base case, and this is usually called the induction step. Okay. And so if we think about it in terms of our stepping stones, we need a place to start, and that's the base case. So we need a place to actually, start our journey. And then we need a way to get from one stone to the next stone. And that's really what the induction step does. This is the, I can get from one place to the next place thing. And this is sort of the simplest tool that allows me to move forward. One of the things that's complicated in the book that we'll come back to after we've kind of worked through this example is the book provides a more general, actually several more general notions of induction that are sort of in some ways better because they're more general and can apply in a variety of situations. But it turns out that for day-to-day practice, these two things are usually all you need. Prove the base case and prove that n gets you to n+1. And if you have those two things, that's enough to get you there. There will be some examples where we need one of the more general versions of induction, but for the starter, actually this is going to be sufficient for most of our initial examples, is that if we have the base case P of 0, and the induction step P of n implies P of n plus 1, that gives us what we need to be able to hop out across the stones going as far as we want. Now, I don't know if that answered the right question or not.
So you're using modus ponens basically.
Over and over and over.
You're looking at the theorem though first to determine like what you need to prove. I guess that doesn't really capture.
Well, in fact, this is pretty general. Like this is not specific to this P.
Right.
In general, if I can prove P of 0 and I can prove n gets me to n plus 1, then this will work for pretty much any P. This will show that P of n is true for all natural n.
Mm-hmm. So you're using a previous theorem though to.
I am using modus ponens, if that's what you mean.
Is that always the case that you use a theorem like that for the proof, or is there a case where it'd be different?
So when we prove these things, I won't actually use modus ponens. I'm using modus ponens to justify that these two things are enough.
Okay.
So modus ponens won't be part of the proof of either of these things necessarily, but modus ponens is what I use to justify that if I say it's sufficient to prove these, and you challenge me and be like, no, it's not. I don't see P of 2 in there at all, right? Mm-hmm. And you're claiming that this gives me P of 0, P of 1, P of 2, P of 3, etc. I don't see P of 2. I can say, no, I can get there because modus ponens lets me take P of 0 and this and get to P of 1. And modus ponens lets me take P of 1 and this and get to P of 2. So modus ponens is sort of justifying that induction makes sense as an idea. Mm-hmm. It won't necessarily be part of the proof of either of these pieces. It's more about why do we even think induction is a rational behavior to engage in? I have no idea if that answered a useful question.
No, I think that gets it. I understand a little bit.
Okay. Now. It's complicated. Like it's totally complicated. So feel free to be like, help. Other questions?
Nick.
Yes.
So if I'm understanding it right, like just a couple of things. So the idea for modus ponens is that essentially it opens the door for all induction proofs.
Yeah, really.
Okay, so it's more like we know that modus ponens allows us to do an induction proof, and then the proof of whatever of this particular example is unrelated to modus ponens.
Correct. So modus ponens allows us to think induction is a rational action.
Okay.
Once we agree with that, then the actual proving things by induction, proving these two pieces, is now unrelated to modus ponens. Modus ponens, I guess, could come up in one of the proofs, but that would be incidental, not sort of, consequential.
Okay. And then, and so the second thing is the second line below the claim is kind of us reworking that first line. Yep.
This line here. So this is just defining P of n.
Okay.
So this is saying what P of n is for some, for any n. Right. And then this is saying the grander thing, namely that all P of n is true for all natural n. So that P of 0 is true, and P of 1 is true, and P of 2 is true, Whereas, well, what is P of 3? P of 3 is the sum of I, 1 at most 3, colon, 2i minus 1 equals 3 squared. So gotcha. This is just sort of a whole bunch of these. And the book is sort of shorthanded this because it just makes it a lot easier than to write this thing, for example, and talk about this down here and this here and this here and this here. So it's useful to have given that a name.
Okay. Sounds good.
Cool. Other questions? These are great questions.
In your where it says we prove two things and then the base case, is that always P of 0 or is it P of n like in your little examples down there?
So that's a great question. It is always P of a specific value. So it's not P of n, it's like P of 1 or 2 or -1 or 7 or something. And it's usually P of 0, but that depends on the quantification here. So this is saying for n at least 0. So this tells us that this is the starting point. So we're starting at n equals 0 in this example. So our base case is P0. We want to start at 0. If this had been n at least 4, which is possible, then we would start at 4. Because we're not saying P of 3 is true. We're saying P of 4, 5, 6, and forward from there is true. So if it was, n at least 4, then this would be our starting point. And our base case would be P of 4. So it does depend on the theorem as to where the base case begins. For most of the examples, that will be at 0, but not all of them. There are examples where we know something's true for n, at least something, that's not 0. So I'm just pulling up my book. If I flip to the exercises at the end, so for example, 12.8, something is true for n greater than or equal to 3. So P of 3 would be the starting point. 12.9 for n greater than or equal to 4. So P of 4 would be the base case there. 12.14, it's actually n greater than or equal to 14 for kind of random reasons connected to the problem. So P of 14 would be the base case there. So there can be situations where the base case is not necessarily 0, but it usually is. So there's a whole bunch of problems in 12.4, and they all start for n greater than or equal to 0. And so all of those, the base case would be P0, because we'd be starting at 0. Did that answer the right question?
Yes.
Cool. Other questions? Great questions. Okie dokie. Then let us actually prove these two things for this particular theorem. So I'm going to make a new page here, and we'll have to copy over some of the stuff so that we've got our pieces in place, but we'll get there. So, we had P of n was the sum over I, 1 at most, I at most n, 2 times I minus 1 equaled n squared. And the claim was basically for all n at least 0, P of n holds. Boom. Proof. And I'll say proof by induction on n. Now, this isn't strictly necessary, but it's useful. Oops, not of. On n ooh, I sort of crossed that out. Sorry about that. It's useful to say I'm using induction and what variable I'm inducting over. There can be problems where there might be multiple variables, and it might be important which one you're choosing to do induction on. That can matter. So as a sort of a communication tip, I would recommend saying, I'm doing a proof, I'm going to use induction, and this is the variable I'm doing induction on. So sort of saying this explicitly in the write-up is probably a good idea. So, so the base case, we need to show P of 0, i.e., and now I'm just going to stick in 0 here, sum over I, 1 at most, I at most 0, 2i minus 1 equals 0 squared. And I should say that in these induction proofs, there's often a lot of copying, right? So I'm copying this down to here, and I'm kind of on the fly substituting in for the ends. There are a lot of like just typo mistakes I can make here. So if I'm like doing a step like this and I wrote n squared here, I forgot to do the substitution, or I got a less than instead of a less than or equal to, like definitely holler. There's a lot of ways I can typo these things. If you see something that looks wrong, definitely let me know. Okay. So this is what we need to prove. So I'm going to start with the left-hand side. So I'm going to say we have sum I, 1 at most, I at most 0, 2 times I minus 1. Now, and notice this is a 2-bar equal because this is a numeric quantity, not a Boolean valued quantity. So I can't use equivalence here. So what do we do to this? How can we simplify this thing? Anybody see anything?
Wouldn't you want the false range rule thing?
Bingo, good job. So why do I want that? What about this speaks to you that says that we ought to be able to do that?
Because you can't have I greater than or equal to 1 and less than or equal to 0.
Absolutely, right? This can't happen. Like if we just think about it on the number line, big fan of number lines. Like I greater than or equal to 1 is, if this is 1, is this part of the world up here, right? And I less than or equal to 0 is this part of the world down here. And those two things just don't overlap, right? There's nobody's in both of those. So this is definitely false. And here, I'll just say by arithmetic, there's a lot of, kind of waffly arithmetic stuff going on because we don't have a good set of rules for doing arithmetic yet. So I can say that. And then, as was suggested, I can use the empty range rule, which is 8.13. So there's a reason I banged on about this earlier, because I knew it was going to come up. Ha-ha. I wasn't just being obnoxious, although I probably was being obnoxious. So empty range rule. So we need the identity for plus, and the identity for plus is 0. And that's what and then 0 is equal to 0 squared by arithmetic, and we're done with the base case. Ta-da! Okay. And base cases are usually pretty simple because you're often just putting in 0 or some small constant for n, and then usually some kind of collapse happens. And it's often the empty range rule. It's not always the empty range rule, but that's a very common thing to have happen. If n is in the range of a quantification, it is frequently the case that the empty range rule, or in some cases the 1 point rule, which is 8.14, one of those is likely to be the thing that gets you to the sort of constant on the other side. Questions about the base case? Okay. Now, okay, we're going to need a new screen. Apologize. On a whiteboard, if we had a lot of whiteboard space, we could make sure we kept all of this up at the same time, but I don't really have that ability here. So if you need me to come back to this page at some point, definitely ask and we can do that. Oh, and so one option I have, and I did this once, but I don't have any evidence that anybody actually taken advantage of this fact. And so I kind of stopped in an effort to reduce the time it takes to process lectures. I can actually save all these as images. That's actually pretty easy. And then I could post them somewhere. That takes a little more time because they have terrible names. And yeah, I mean, they're basically like image 1, image 2, because how does Zoom know? But if it would be useful to have these as images, I mean, they're in the videos, but if it'd be useful to have these as just standalone images, I could do that, right? You just need to tell me that that's a priority. So I move it up the list of things that, needs to be done on any given day. So feel free to say something now or on Slack or whatever, if you have thoughts on this. Okay, questions before we make a new screen and do the induction step? Okay. I'm going to rewrite P of n at the top again. I won't do the rest of it. So the sum over I, 1 at most n, 2 times I minus 1 equals n squared. And so now we're at the induction step. Where we're saying, so we need to show P of n implies P of n plus 1 for all n at least 0. Okay. And so the way we typically do this is we say, assume P of n holds. So this is assuming the antecedent. So this is basically assume the antecedent from chapter 4. That should have an S. Antecedent. And prove P of n plus 1. So this is, these induction proofs almost always have this form. We'll assume P of n is true, and then we use that to prove that P of n plus 1 is true. Okay. You could take the whole thing and show that it's equal to true, but if you think about it, P of n is all of this. P of n is all of this with n plus 1 and n plus 1 here. So this implication would be a lot of writing. So it's easier usually to assume the left-hand side and then prove the right-hand side is equivalent to some true statement. So that's what we're going to do, okay? So, questions about the setup before we actually then do things. So our goal is to prove P of n plus 1. Let's actually write that out, i.e. sum over I, 1 at most n plus 1, 2 times I minus 1 equals n plus 1 squared. Now, it's critical that we get the parentheses here around the n plus 1. This is a common source of mistakes where people will substitute in n plus 1 and forget that it needs to like stay as a unit and get their parentheses in the wrong place. And in this case, like without the parentheses, I'd have n plus 1 squared, which is definitely not the same thing and definitely not what we want. So we need the quantity n plus 1 squared. So I need to prove that. So I'm going to start with the left-hand side because the left-hand side is clearly more complicated. So using the heuristic of start with the complicated part, this is pretty clearly uglier than that. So let's go there. Sum over I, 1 at most n plus 1, 2 times I minus 1 equals, Does anybody have a suggestion for what we might do here?
Split off term?
Bingo, full marks. So in the same way that we wanted to use chapter 8's empty range rule on the base case, when we're doing the induction step, we very frequently, again, if the n plus 1 is in the range, we very frequently want to use split off term from chapter 8. So both of those rules that I kept like assigning stuff on actually turn out to be really important here. So split off term, we can use 8.23a. 8.23a. And we're going to have the sum over I, 1 at most n. So we're going to peel off the n plus 1 term and be left with the n up to the n term. And then we're doing plus because sum is just another word for plus. And then we want the n plus 1th thing. So we want this with n plus 1 for I. So we want 2 times n plus 1 minus 1. And this is a place where people frequently get confused. Is you got to be careful about what's your last term and make sure that you go from here to here correctly, and that you split off the correct term here. And if this had been a less than n plus 1, then this would have been an n, and this would have been a less than n, right? So you've got to like read this carefully and think about what that means in the context of the proof that you're trying to do. But yeah, this is the basic idea. And the reason this is useful is now this matches the left-hand side of P of n, and we're assuming P of n is true. So that gives us some nice things we can do. But questions about this step before we go forward from here? Going. Okay. Now, this matches, here, let me give myself a different color. So this matches this. And we're assuming that P of n is true. So that tells us that we could replace this with that. And that's what it means here to assume that P of n is true, is that we ought to be able to replace any occurrence of this with n squared, or the other way around. And since this matches exactly, we ought to be able to say by assumption P of n, this is n squared plus 2 n plus 1 minus 1. So we've gotten rid of the quantifier. This is a huge step. And this is usually what the using the assumption does for you, is it allows you to eliminate the quantification and replace it with something that doesn't have a quantifier in it. So you're using split off term to simplify the quantification so it matches the assumption, and then the assumption allows you to rewrite the quantification to something that doesn't have a quantifier in it. Does that make sense? Questions? And this pattern's really common. So split off term and then use the assumption. That basic structure comes up a ton. Not every time, not always exactly like this, but it is super frequent. So, you know, think of, people want to make these induction proofs really hard. And in fact, they're often fairly formulaic. And if you just kind of remember the recipe and go through those steps, it often will just work out. You have to be thoughtful about things like, well, what actually is this value? And what exactly is this operator? And what does that tell us about what term we're splitting off? This is a common problem. But if you're careful about those kinds of things, well, what rule do I use is often not a question you need to be thinking hard about, because it's often split off term, then use the assumption, and then clean up by arithmetic or what rules that you know about the world. And that's very often the form that these things take. So does that make sense? Questions before we continue? Okay, so now we're down to just some arithmetic. So we want to get to n plus 1 squared, right? That's what we're trying to get to. So we're hoping that we can get this to n plus 1 squared. So let's actually expand this middle bit and do a little algebra. And you're all so thrilled to be using algebra again after having hoped to avoid it forever. It comes up because algebra actually is important. So 2n plus 2, so I've just distributed the 2 across. And now I can do the, I'm gonna try to stay all on this screen. So I will go over here, you know, equals, and now a little arithmetic. That 2 minus 1 is 1. And now here again, I have to use a little algebra. And this is n plus 1 squared. And there we're at the end. So we're done with the induction step. And that completes the induction proof, because we've proved our 2 pieces. So QED. Wah, 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 yay. That's a lot. Questions? And as a heads up, it is very common that people get bogged down in this algebra stuff at the, oops, didn't want to put a mark there. In this algebra stuff that at the end, that in some sense is the simple part. I mean, this is all like from high school or something. But if your algebra skills are rusty, this stuff can actually be a real nuisance. And one of the homework problems, in particular, exercise exercise 12.13 has a fair bit of algebra in it, and people often get sort of tangled up in that. So if you're concerned about your algebra skills being rusty, I would definitely start this whole thing early, so that if you get stuck on an algebra thing, you can just ask a quick question. Because this isn't a course in algebra, I'm quite happy to give you pretty hefty tips on the algebra side of things. But you know, that works better if you start early and have time to ask questions. Okay, so questions about the proof of the induction step. There's a lot going on here. So we needed to show P of n implies P of n plus 1. We assumed the left-hand side, the antecedent, and then we proved the right-hand side. So we're using that technique from chapter 4 that says to prove an implication, it's okay to assume the left-hand side is true for the purposes of the proof, and then show that the right-hand side holds. So we needed to prove this. And so we started with the left-hand side. We did split off term, which is very common. That gave us something that matched the left-hand side of P of n. So we replaced that with the right-hand side of P of n. So actually, why don't I also underline this in green? And then all of this stuff just carried down. Then we'd gotten rid of the quantification, and then it was just a matter of doing some algebra to get to the n plus 1 that was the target right-hand side. And that finished the induction step. And that plus the base case from here was enough to do the whole induction proof. And we have proved that this is true for all n. We proved it was true for 0, well, all n greater than or equal to 0. We proved it was true for 0, and we proved that if it's true for n, it's also true for n plus 1. So we can get from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. So for any finite value, I can, in a finite number of hops, get from 0 out to that value. It might be a very big number of hops, but it's a finite number of hops. I can get there and be like, ha, done. I have proved it. And so we'll just take that as being sufficient to prove it for all n greater than or equal to 0. Okay. Questions about all of that? Going. Okay. So there's some cleanup that we have to do here. And we've got a little less than 10 minutes. So I'm going to do one small piece of cleanup now, and then we're going to go back to the way the book phrases induction on Wednesday. And do some more examples. But I'll do one quick piece of cleanup here. And that is, how did we actually deal with this bit here? Because there's actually a quantifier in this statement, and we didn't seem to have done anything with quantifiers. Like, we were really, if we wanted to be careful, like, this really is for all n n at least 0 p of n implies p of n plus 1. But I kind of totally seem to have cheated here. Like I didn't do anything about quantification anywhere in this. At least no for alls. I'm gonna have my summation still, but there's not a for all anywhere in this. So how did I actually prove this quantification without actually doing any quantification stuff? That seems like I cheated. So I didn't cheat. I actually used something that we talked about a long time ago, but which we didn't really do anything with. And I said we'd come back to it later when we needed it, and now's the time that we need it. So I'll say a little bit about that. So I'm going to make a new page because we don't have any room to write anything here. What I was trying to prove, to repeat that, was for all n at least 0, p of n implies p of n plus 1. Okay. And for reasons which will become clearer in a second, I'm actually going to use trading here to give myself true in the range, because that'll be important. So I can move that n at least 0 over here and say it implies that the implication is true. And if I wanted to, yeah, let's do that. Let's do shunting as well. Well, actually, there's probably a trading rule that would have done this. Trading. Where are the tradings? No, I lied. So I'll use shunting now. For all n at least 0, and p of n implies p of n plus 1. Okay, great. All that's very exciting. Now, what we really care about, though, the point of this little digression, is we had meta theorem 9.16 that we talked about a little bit, but then we didn't do anything with. And I said, hey, that's just good. Oh, whoa, stop. I clicked a thing and I broke the world. Okay, thank you. Oh, stop it. Terrible pen control today. Meta theorem. And I said, this will come up later. Well, now is later. So, and 16 says P is a theorem if and only if for all x, P is a theorem. So what the and that has this form, like all of this is the P here. That's why I moved everything out of the range so that this would match. So this says that this if and only if means that I can prove this by proving that, or I can prove that by proving this, either way. And in this case, I'm simplifying back to this. So to prove this quantification, I can prove P, the body, n at least 0 and P dot n implies P of n plus 1 for arbitrary n, and that's kind of an important piece here. So I have to make sure that I'm not using a variable that means something somewhere else, like it's not always 7 or something like that. So I have to be a little careful about that, but assuming that I'm not making any particular assumptions about n, if I can prove this, that's enough to prove this quantification. And that's how I get away with just proving that P of n implies P of n plus 1. P of n implies P of n plus 1 without doing the whole for all business, because meta theorem 9.16 tells me that that's okay, that if I want to prove this for all, it's enough to just prove the body, okay? And I actually wasn't explicit about it, but this is actually true because that's in the assumption of the problem for n at least 0. So I have that this is true, and then I want to prove that implication. So that is where this meta theorem turns out to be important, is I don't want to have to write this whole quantification all the time. So the meta theorem lets me sort of strip out the quantification and just focus on the bit that I care about, which is the implication that I need to make induction work. Okay, that's a little weird. Are there questions about that in the 1 minute that remain, or questions about any of this induction stuff?
So do we have to do like the meta theorem 9.16 thing before we start our proofs?
So I would say no, I don't require it in the write-up. And I won't usually actually say anything about it explicitly, but you do need to understand how it's being used. And like I might have a question on a homework or something that's like, explain how meta theorem 9.16 is being used to justify this approach to proving this thing. So you do need to sort of understand this, but I'm not going to expect you to write this whole business out over and over and over again, because I think that would just be tedious. What I've done here is pretty much what my write-ups are going to look like and what I would expect your write-ups to look like. Does that make sense?
Yeah, that makes sense.
Cool. Other questions in the 0 minutes remaining? I have to make sure I give you time to walk to your next class because it's probably a long trip. Going. Pleasure. I will see everybody on Wednesday. And definitely have a look at the quiz, and we'll do questions and things about that on Wednesday as well. So, ciao.